All right, here we go. Lesson 6.5, we're going to learn how to solve exponential equations. And just to give you kind of a little introduction before we do like the full wacky little note page, the Common Core, or the Common, what's it called? Core concepts, that's what they're called. I just want to introduce like what an exponential equation is, what they mean, what they look like, right? So an exponential equation, really, if you boil it down, it just is an equation that has the variable in the exponent. And I put a couple, these are like in my mind, like these ones kind of like cement it for me. Like sometimes it's easier to catch a concept when you see concrete examples of it first. So this equation right here, 2 to the x equals 8. So it's basically just the x in the exponent is just telling us the question that this thing is asking is 2 to what power gives you 8, right? So who can solve this just like in your head? What would x equal? Like how many times you're going to multiply 2 by it? 2 times 2 is 4, times 2 again would be 8, right? So 2 to the third power would be 8. So that means, so like one way to solve this, like kind of in your head, is to say, well, all right, 2 to the third power equals 8. It's kind of like before when you could be like x minus 7 equals 2. And some people could just look at that and go, well, doy, x is 9, right? Because 9 minus 7 is 2. So, but then we also looked at like, instead of just looking at equation and letting your limbic brain solve it, we actually said, all right, algebra is about like, what steps do we do to solve things? So then we said, oh, well, we could add 7 to both sides and that would give you x equals 9, right? So we're going to also learn the steps that we can do to solve these when they don't look obvious, right? So here's 2 examples that should look obvious, right? 3 to what power equals 9? Well, 3 to the second power, right? So y would equal 2. So there we just solved a couple of exponential equations just by looking at them and thinking about them, right? But we can also turn this into like an algebraic process, and because behind the scenes, what we can write out what's happening by saying like this: 8 is the same as saying, we can rewrite 8 as a power of 2, right? 2 to the third power is 8. And so if you're able to, so one of the rules that we're going to learn, or the methods that we're going to learn, is if you're able to rewrite both sides of the equation as a power of the same base, then the exponents have to be equal. 2 to the x equals 2 to the third. The only thing x could be is 3, because 2 to any other power is not going to equal 2 to the third, or 8. Okay, so then here is their version of that, with all the algebraic rules included, right? Exponential equations are equations in which variable expressions occur as exponents. So in regular English, variables in the exponent. That's how you are going to identify whether something's an exponential equation or not, are the variables in the exponent. Okay, and then the core concept is the property of equality for exponential equations. 2 powers with the same positive base, where the base is not equal to 1, are equal if and only if their exponents are equal. So that's like, so in numbers, how you would write that is like this: 2 to the x equals 2 to the fifth, then x has to equal 5. If they're the same base and they're equal, then the exponents have to be equal too. La 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 la. And then in the algebraic words, if b is positive and not 1, then b to the x equals b to the y, if and only if x equals y. So this is basically the book's way of saying what I tried to introduce a little more what's the word, casually. This is very formal and official definitions down here. On the last page, this was just like casually talking about exponential equations. Okay, so let's do some examples. So the idea that we're going to use to solve these is that if what we just talked about, if you have the same base, then the exponents have to be equal to each other. So I just want to kind of give you guys some visual cues here. So here we got an equation that has two powers, right? Same base. The base is 3 on both of them. So that means that the exponents have to be equal to each other. So right now we can say, and essentially like that we come up in math, we come up with descriptions of what we're doing. Like if we are dividing both sides by the same number, sometimes we'll say things cancel out, but really it's, so you might say like, oh, you kind of just drop the bases off, because the next thing you're going to write is the exponents have to be equal to each other. So you're going to write x plus 1 has to equal 5. Right? So it's almost like you're a DJ and you drop the bass. Okay, so then once you just drop the bases and set the exponents equal, then it's just regular solving. We're going to subtract 1 from both sides, and we get x equals 4. And then it'll make sense if you think about plugging that back in. If you plug a 4 in for x, 3 to the 4 plus 1, well, that's 3 to the 5th. Okay, then our next equation, we've got 6 to the 2x minus 3 equals 6. And you might say, well, hey, there's no exponent on the left side. But if you think about it, 6 to the first power is 6, right? So there's an invisible power of 1. So then what we say is, all right, the bases are the same, so the exponents have to be equal. So 1 has to equal 2x minus 3. So then it's just a regular little dude we're going to solve. Add 3 to both sides. Then we get 4 equals 2x. Divide both sides by 2. Because that'll get us x by itself. 2 divided by 2 is 1. So 1x on the right side. So that's just x. And then 4 divided by 2 is 2. So for this one, x equals 2. Right? And if you think about plugging a 2 in for x, 2 times 2 is 4. 4 minus 3 is 1. So they would have the same exponents. Then on C, we've got the base is 10 on both sides. So the exponents have to be equal to each other. So then our next step would be to say that 3x has to equal 2x plus 3. Then we've got x on both sides, so we need to subtract it off one side. So I'm going to subtract 2x from both sides. Three x minus 2x is x. So we get x equals 3 for this one. Okay. So the next kind of example, the next kind of problem that we're going to look at, I believe, is when they don't have the same base, but we can make them have the same base. We can adjust them a little bit, right? Write them as a different power or something. Okay, so if you get an exponential equation and you don't have powers with the same base on each side of the equal sign, then first you have to rewrite each side of the equation using the same base. So let's look at some of these. So let's do, oopsie. So for this first one, 5 to the x equals 125. So I don't have like 5 to the x equals 5 to the something, but I can rewrite 125 as a power of 5. Right? This goes back, remember the little list of numbers we made with the powers and stuff? You can just use that list as a reference, and any number you see on that list, you can rewrite as a power, right? 125 is 5 times 5 times 5. So we can rewrite the 125 as 5 to the third power. And now we have an equation that has same bases, so the exponents have to be equal, so then x has to equal 3. For b, we've got 4 to the x equals 2 to the x minus 3. And so these are different bases, but can I write them as powers of the same base? And I can rewrite 4 as 2 squared, right? So instead of 4 to the x, I can rewrite the 4 as 2 squared. And then I'll leave the right side alone because this is just 2 to the x minus 3. And then I need to remember my exponent rules, right? I have a power to a power right here. So what do I do with these exponents? Power raised to a power, we're going to multiply the exponents. If you have power, like if it was like 5 squared times 5 to the third, you would add those exponents. That would be 5 to the fifth. But if it's like 3 squared to the fifth power, you would multiply the 2 times 5. That would be 3 to the 10th. So right here, we're going to multiply the 2 and the x. So this is 2 to the 2x power equals 2 to the x minus 3. And now that we have same bases, we can set the exponents equal to each other, just like we had over here. Same bases, set the exponents equal. So I'm going to say, all right, then 2x has to equal x minus 3. Then I'm going to, I have x on both sides, so I'm going to subtract it off of one side. But you have to do the same thing to both sides of an equal sign. So we get 2x minus x is x. So x equals negative 3. Then for C, we've got 9 to the x plus 2 equals 27 to the x. Well, let's see. 9 and 27 are both powers of 3. So if I'm going to just say, all right, I'm going to replace the 9 with its power of 3. And I'm going to replace the 27 with its power of 3. So 9 to the x plus 2 becomes 3 squared to the x plus 2. 27 to the x, that's 3 to the third to the x. Now, there's a little nuance here that you have to remember. You have to remember, okay, we talked about how if you have a power raised to a power, you multiply the exponents. But you got to remember, since this exponent is a binomial, has two terms, we have to distribute when we multiply, right? 2 times parentheses x plus 2. So I'll write the extra step here. So this is 3 to the 2 times x plus 2. And this is 3 to the 3 times x. So now I have to distribute the 2 up here because these two exponents are multiplied by each other. So this 2 has to get multiplied by the x and the 2. So then we get 3 to the, let's see, 2 times x is 2x. And then 2 times 2 is 4. So now we have same bases. So we can set the exponents equal to each other. So 2x plus 4, and I'm going to write them up here. Two x plus 4, this exponent has to equal 3x, the other exponent. So I'm going to subtract 2x from both sides because I don't want x on both sides. And I get 4 equals 3x minus 2x is x. Okay. Okay, so now we'll look at a couple of examples when the b value is between 0 and 1, but base. All right, so first let's look at part A over here. We've got 1/2 to the x equals 4. And what we're going to do is we're going to use that same strategy we just did. We're going to try to write each side as a power of the same base. So when you look at these numbers, what base comes to mind? Like 4 is 2 to the second, and 1/2 is 2 to the -1, right? Because negative exponents just flip the base, right? So I'm going to rewrite my 1/2. So my 1/2, I'm going to write, so I'm using the fact right here that 2 to the -1 equals 1/2. So 1/2 is 2 to the -1, so I'm going to put 2 to the -1 over here. And then I'm also going to rewrite my 4 as 2 squared. Now I have a power raised to a power on the left side here, so -1 times x. So this is going to be 2 to the -x. And now we have same base, so we can set the exponents equal to each other. So -x equals 2. So then if you just multiply both sides by -1, then we get positive x equals -2. Okay, so then when we look at the equation we have for b, 4 to the x plus 1 equals 1 over 64. Let's see. Is 64 a power of 4? It is. 4 times 4 is 16. 16 times 4 is 64. So 64 is 4 to the third. So I'm going to do that right now. I'm going to rewrite 64 as 4 to the third. And then can I write 1 over 4 to the third as just a power of 4, not a fraction? If I bring the base up, what does that do to the exponent? Just makes it negative. So if I bring the base up, this would be 4 to the negative 3. And now we've got the same base on each side, so we can set the exponents equal. So we get x plus 1 has to equal negative 3. Then we subtract 1 from each side. And we get x equals negative 4. And then the last thing that we're going to do is I'm going to show you how to use a graphing calculator. We're going to use Desmos to solve equations that we can't do any other way with algebra 1. Like if we cannot write them as powers of the same base, then we have to use a graphing calculator to solve these. And so if you look at A, we got 1/2 to the x minus 1 equals 7. Now I could rewrite the left side as a power of 2, but I can't rewrite the right side as a power of 2. So what I'm going to do is I'm going to graph each side of the equal sign. So each side of the equal sign is going to give me a different thing to graph. And what I'm going to do is I'm going to say for this one, I'm going to graph y equals 1/2 to the x minus 1. And on this side, I'm going to graph y equals 7. And then all I have to look for is the point where they intersect. And I'll tell you what the y value is going to be. It'll be 7. But then once we figure out what the x value of that point is, that is the x. That's the solution to our equation. Okay, so let me open up a Desmos. And I'm gonna graph these. I'm gonna do y equals 1/2 to the parentheses x minus 1. That was it, right? Yeah, 1/2 to the x minus 1. And the other one is y equals 7. I got to zoom out a little bit to find my y equals 7 line. And then all I got to do is find the point where they intersect. And the x value is my solution. So negative 1.807. And it rounds it. This is really like probably a really long decimal number. But 1.807, that's what we'll put. Negative 1.807. So we got x was equal to negative 1.807. Woo. And then for this one over here, like the right side doesn't even have x in the exponent. It doesn't have a power at all. So what we can do here, same strategy, is just graph y equals 3 to the x plus 2, then graph y equals x plus 1 and see where they intersect. So we're going to do y equals 3 to the x plus 2, and we're going to do y equals x plus 1 and see where they intersect. Y equals 3 to the, now if you don't write parentheses and you just say, what was it? X plus 2. If you just type x plus 2, look what happens. Oh, wait. 3 to the x plus 2. See how it puts the x up in the exponent, but then it leaves the plus 2 down there? So we don't want that. We need the plus 2 to be in the exponent. So what we have to do is you have to do parentheses, then x plus 2, then close the parentheses. And then the other thing we're going to graph is just y equals x plus 1. Oh, what do you notice here? They don't intersect ever, right? So there is no x value where these y values are the same. So this, our original equation has no solution. All righty.